motor car has a future, but the car of the future has to be even faster, safer, and more comfortable than ever before. And so we can no longer rely on the old traditional methods of building it. Decades of experience in automobile construction are not enough. In order to eliminate human failings, experience must be combined with modern data processing. And, as is the case in the spaceflight program, material and construction subjected to stringent controls. The computer is playing its part in helping to build the car of the future. This car is the C111. The requirements for its development were a sports car not more than 43 inches high, with wheelbase 8'6", wheel track front 4'7", back 4'5", a Wankel engine in the middle, a speed of more than 160 miles per hour. Its styling was to be futuristic, its development considerably shorter than had ever been the case before. This would have been a very difficult task had engineers just relied on previous experience, for there is little which is relevant to such a vehicle. The calculations could keep 20 of the best engineers at work 500 years from now, but with the assistance of electronic data processing, engineers had access to completely new fields of information. This development process ranks as a unique achievement in the automotive industry. All calculations from A to Z were completed in barely 4 months. Practical tests were only undertaken in the final stage. The projected goal was reached. Maximum stability with minimum weight. A car of the future, calculated on an IBM computer with Esem.
Well, Esem must certainly be a very famous man.
Esem is an elastostatic elements method, by which complicated structures are broken down into small elements which can be expressed mathematically, and with the help of compatibility equations can be converted into a system of linear equations.
I don't understand that. Much too difficult.
Let's put it more simply. What driver doesn't get annoyed at the squeaking, thudding and rattling in his vehicle on bumpy roads? Yet every vehicle on the road is constantly subjected to vibrations. On all rough surfaces, in every curve, every time acceleration or braking occurs, strains are produced, which create enormous stress. The vehicle's resistance depends on how rugged each of its individual parts are. Of course, we're including critical situations here as well. Rigidity means strong where necessary, less resistant where possible, not too light and not too heavy. Let's take a bow, for example. It must be able to withstand the greatest stress at the center, and there it is thickest. It's thinner at the ends, because the stress is not so great here, and more elasticity is required. A bow that is rigid and yet elastic has more chance of shooting further than one which has neither of these qualities. Thus, elasticity and rigidity in the right places, together with the most useful weight, achieve optimum results. This optimum result, naturally, also has to be achieved in automobile design.
As you no doubt know, the bodywork of a car is a steel skeleton of tubes and panels. In order to be rigid, the strength of the individual parts must be coordinated to the stress each part has to bear. So each individual part must be calculated exactly. For this, a model is made, which can be sectioned off into triangles, rectangles, and squares. And so you see, in order to ensure that what now looks like a lattice will still be comprehensible, later on, the points where the geometric shapes meet are given numbers.
In the original drawing, we get a reference system of X, Y, and Z coordinates. If we now, for example, want to work on a skeleton electronically, then the diagrammatic values must first be registered on punch cards. This takes place on the so-called digitalizing unit, with a card puncher attached. The numbered drawing on the table is scanned by the sensor. Coordinates and numbers of every point are punched into the cards by pressure on a foot-operated switch. The electronic reader now takes the data from the punch cards and passes it on to the computer, which stores it on magnetic tape. And now the automatic part of the ASEM procedure starts. But before this, another check is made for any mistakes made during the punching of the cards. This can be done by the computer itself, by an electronic stylus called a plotter, or over a screen. First, the computer. It has found a mistake. This mistake is identified by a number and recorded on the list of mistakes. Its meaning can be read from there. A card was incorrectly punched, and this must be rectified. The computer immediately records the new numbers on the magnetic tape. Now, checking is continued on the screen. The drawing appears again on call. By pressing a button, enlarged or reduced forms can be viewed, or projections or outlines selected according to which particular point is to be checked. Here, the observer can see that a point has been incorrectly programmed and corrects it with an electric stylus. He alters the number for this point from 138 to 118. This correction, too, is automatically transferred onto the computer's magnetic tape. Finally, there is one last check. The information on the magnetic tape is fed back to the automatic drawing device, the plotter.
Once the plotter's diagram corresponds to the original drawing, and all the discrepancies are finally corrected, the second and more exciting phase of the ASEM process begins. Now, the computer should inform us what stresses bear on the individual components of the bodywork. The effects of torsion, deformation, and one-sided stresses will be examined, and it'll indicate which structural parts might possibly have to be reduced or maybe strengthened.
But in addition to information about shapes and outlines already at hand, it also requires data on cross-sections and material. This data is also transferred onto punch cards and stored on the magnetic tape. The picture now gradually turns three-dimensional. Further checking, and if necessary, correction. If it weren't for this ASEM procedure, a developmental model would have been needed to study reactions to definite stresses. This would have required painstaking work. The computer has the solution in 8 minutes. It gives the deformation values and shows by asterisks which surfaces or supports are important and which not so important. The more asterisks, the greater the stress. This deflection curve, for example, would have required long practical experiments. ASEM produces the results after brief calculations. What otherwise would have involved time-consuming tests on the jolted track is shown on the computer's screen long before the car has been built. The numbers fed into the computer make it possible for the vibrations to be seen on the screen. With this data, designers can now produce a model corresponding to the calculated values. They can be sure that it is exactly what is required. But the technical and stylistic demands have yet to be reconciled. Designers and engineers must cooperate to find the best solution. Much will still have to be modified, and many more experiments carried out. But a start has been made, and the first version of the bodywork begins to take shape in the workshop.
Here, those numbers and signs that you saw on the magnetic tape have really come to life.
Fantastic.
A car is born. The first driving tests prove that a new research technique can supplement old proven methods. A new generation of automobile engineers is developing methods to realize the sportsman's goal: faster, further, higher, used in an extended sense to apply to technology and industry. There is no inherent contradiction presented by tradition and progress. The important thing is to make them work together.